lesson, we will be discussing topological sort, cycle deduction, connectivity, and spanning trace. So, with topological sort, so let's look at the graph here. The given graph um, represents the list of courses and their prerequisites. For example, course 142 is a prerequisite of 143 and course 143 is a prerequisite of many other courses like 321, 341, 370, 378, so etc. So all the vertices represents the courses and the edges with the direction because it's a digraph. So all the edges represents the sequence. So which comes first, which comes later. Like after taking 142, the next course is 143, something like that. So in some situations, you have to do some task before doing another task. Like here, you have to take a course 142 before taking 143. Prerequisites, is it? But looking at the graph, because you know already graph is a non-linear data structure, by seeing this graph, you may not easily understand the sequence. Like I want to take the course 341. So what should be the prerequisite? It's not that clear enough to see and understand the sequence. Okay. So is there any way to linearly arrange the courses here in the graph, to linearly arrange them in the order they should be taken? Linearly arrange them, meaning is in a sequence, one after another in a sequence. Because graph is a non-linear data structure, can you show the same graph in as like a linear data structure, as like a linear way? Okay, well, like one after another. Can you able to convert this graph in a linear sequence? Yeah, we can do so using topological sort. Okay, we can convert them to an acyclic graph. Okay, directed acyclic graph. So how do you do? We are going to use topological sort. It's a method of arranging the vertices as a sequence. So no vertex appear in the sequence before the predecessor. Okay, predecessor will come first and then the successor and then the successor. So you won't have the vertex coming before the predecessor. No. So let's look at the topological sort here. So the above graph, the graph on the top, can you see it's A? So the graph in figure A can be topologically sorted like the one given B. Okay, then directed acyclic graph. Okay, let's look into that the topological sorted graph. Can you see here? It's linearly arranged. The vertices are linearly arranged. So easy to understand. I can easily say which is the prerequisite for the course. Like for example, 321, the prerequisite is 143. Okay, for example, I want to take 401, the course 401, it has 4 prerequisite, 378 and then 341 and then 326 and then 322. Can you get the idea? So it's linearly arranged. The vertices are linearly arranged using topological sort. So easy to understand. So what comes first, what comes next, something like that. Okay. So topological sort. So we are going to discuss about that. How are we going to do that? Let's see it. So before that, keep it in mind, topological sort is not unique. So given a graph, so there is a graph given in this slide. Can you see? So all topological sort of the graph is given in the right hand side. Can you see S1, S2, S3, S4? So these are the topological sort derived from the given same graph. So keep it in mind, topological sort is not unique. That means you're not going to get one topological sort from a given graph. You may get many. This is one example. So let's see how we are going to do the topological sort, the algorithm. So the algorithm for topological sort is very simple. We have to find a vertex, okay, with no incoming edges. What do you mean no incoming edges? No inward edges to the vertex. Okay, that means 0 in degree. Okay, add the V, that particular vertex, to the sorted list and disregard the V from the graph, remove it. Let's remove it. And all the edges coming out of that V. Okay, so just understand this. We need to identify the in degree of each vertex. First of all, given a graph, calculate the in degree for each vertex. So you may have some vertex or some vertices with 0 in degree. So one by one, you need to remove the vertex with 0 in degree, and you are going to add it to the sorted list. Remove and put it in the sorted list, and there may be edges coming out of that vertex, is it? So remove that also, and then recalculate the in degree for the remaining vertices and do the same. Find out the vertex with 0 in degree, add it to the sorted list and remove the outgoing edges. Okay. Sometimes in a graph you may have more than one. Okay, so this is the algorithm. Sometimes you may have multiple vertices with degree 0. So in that case, you can actually visit them, because I told you you need to identify a vertex with no incoming edges, meaning is 0 in degree, and add it to the sorted list. In case if you have multiple vertices, which one you are going to choose first? Actually, you can go in any order, but in order to get a unique answer, okay, so we are going to follow some idea, some technique. We are going to visit them alphabetically. So we are going to visit them, add it to the sorted list in an alphabetical manner. Let's assume that you have two vertices with in degree 0, A and E. So don't take them in any order, just take it in alphabetical order. So visit A and then E, something like that. Okay, let's example. Assume that this is your graph. It's a digraph. Okay. So we have these many vertices A, B, C, D, E, F, G, H, I, J. First of all, you need to calculate the in degree of each vertex. What do you mean by in degree? How many incoming edges are there for each vertex? Incoming edges. How many? How many? Count of incoming edges for each vertex. Can you see? Incoming. So the vertex D, there is no incoming. So it's 0. Vertex E, 1, 2. Okay. For F, it's only 1. For G, there is no. Can you see 0? H, it has 2. I also 2. J, there is nothing. In degree is 0. In degree means count of the incoming edges to that vertex. Okay. So now you calculated the in degree of these vertices, and the algorithm says you need to identify a vertex with 0 in degree, and then you need to add it to that sorted array. Okay, so here we found 3, D, G, J. Actually, you can visit them in any order, but to get a unique result, we are going to visit them in alphabetical order. So D comes first. So let's visit it. Okay. And the algorithm says after you added that vertex into the sorted list, so I added to the sorted list, you remove it from the graph. Just remove also the outgoing edges. Can you see? It's all highlighted in red color. Remove that also. Okay. So now you need to recalculate the in degree of the remaining vertex, because you removed the edge. You removed. Okay. So now I recalculated. So we have two vertices with 0 in degree, G and J. So alphabetical order. G comes first. So put it in the sorted list. Remove the vertex with the outgoing edges. Not only outgoing edges. Okay. Now the next one is J. We recalculated the what do you call the in degree of the remaining vertices, because we removed. So we need to recalculate. Now we have two, A and J, alphabetical order. So A comes first. So put it in the sorted list and then remove the vertex with the edges and recalculate. Now we have F, B, J, alphabetical order, and remove the vertex with the edge. Now recalculate. Now we have 3, F, H, J, obviously alphabetical order. F. There is no edge from the F, so it's okay. Here comes next to one is H. Remove it from the graph. Recalculate still the same. Now J. Remove it. Recalculate the degree of the remaining vertices. So now I have only one E. So visit means you need to add it to the sorted list and remove it from the graph. Remove the vertex with the edges. Now recalculate in degree. I remove the vertex with the edges. And the remaining, when I recalculate, there is no in degree for C. So the sorted list. So this is the topological sort for the given. So what is the, let's see, this is the graph and this is the topological sort. So what does it mean, topological sort? You are linearly arranging the vertices in a sequence, arranging the vertices in a sequence. So this is the topological sort. Okay, let's put it in a acyclic graph. So this is the directed acyclic graph. Can you see DGA BF? Can you see DGA BF HJEIC? So this is the sequence of the vertices. And then you just add the edges. You can take it from the graph. A to B we have something, and A to F. So G to B. So add the edges. So now you can easily understand what comes first and what comes next. What is the successor? What is the predecessor? You can easily have an idea. So this is the way how are you going to do the topological sort. Okay. So this is another example. Maybe you can try it out later how to do it. When you follow the algorithm, you will get this sequence for the topological sort, and this is your directed acyclic graph. Now let's see the cycle deduction. An easy way to detect the presence of cycle in the directed graph is to attempt a topological order traversal. Okay, so the algorithm visits all the vertices of the digraph if the graph has no cycles. If there is no cycles, all the vertices in the digraph are visited. So, for example, let's look at the graph. Here in this graph, after the vertex A is visited and it's removed, when you try to visit this vertex A, because how do you say, a few minutes ago we say that if the vertex is having a 0 degree, you just add it to the sorted array and then remove it. So when I add the vertex A and remove it, what will be the degree of other vertices? B1, C1, D1. So what to continue? Because if I have a vertex with 0, I will add it to the sorted array. But all the remaining vertices B, C, D will get 1. So that's it. I cannot proceed the algorithm. The algorithm stops. How the algorithm works? The algorithm works with the vertex with the degree 0. Here I am not getting any degree. After I visit A, after I add the A to sorted array, all the remaining B and C and D will get a degree 1. So I cannot proceed. What does it mean? It means that there is a cycle. So that's the idea. Okay, so this is the way we can identify the presence of cycle. Okay, so the topological sort cannot be completed because there is a cycle. Yeah, so connectedness, I told you, a graph is said to be connected if there is a path between every pair of vertices. There is a path, but given graph, so this graph, the one given in the slide, it's one single graph. Don't think there are two graphs here. This is one single graph. There is no path between B to D or B to E or B to F, or C to D, C to E, C to F, or A to D, A to E, A to F. There is no path between these. So this graph is not a connected graph. Okay. So when you're talking about connectedness, how can you test the connectedness in a simple graph? You can use the traversal, depth first, breadth first traversal. So when you use any of these traversal, when you visit all the vertices, that means the graph is connected. When you miss out some vertices, that means the graph is not connected. In a directed graph, there are two types of connectedness. A digraph can be a strongly connected digraph or weakly connected digraph. Strongly means there is a path between every pair of vertices. Okay. When I say weakly connected, if you ignore the direction, there is a path. But if you consider the direction, there is no path. That is the meaning. There is a difference between these two. Strongly connected means there is a path between every pair of vertices from A to B and from B to A. Can you get the idea? From A to C, if you have a path, from C to A, you may have a path. Okay, every pair of vertices. In weakly connected, if you ignore the direction, you may have a path. Okay, so that is weakly connected. See here. So here we have a path from B to E, but there is no path backwards E to B. So path, not the edge. I'm not talking about the edge. Path. Path means I can go from E to F, F to D, D to B. No, I don't. D to E only I have. E to B I don't have. You know, so it's you know, I should not visit it. Okay, so there is no path from E to B backwards. Can you get the idea? So this graph is not a strongly connected graph, but if I ignore the directions, let's ignore the direction. If I ignore the direction, I will get a path. I will get. So that's called weakly connected. Okay. So this graph is weakly connected because the simple graph is connected. You have a path between every pair of vertices. You get a path, but you just ignore the direction, you will get path from A to B, B to A, from A to E, E to A, from A to F, F to A, something like every pair. Okay. So let's talk about the spanning tree. Let's assume a graph. It's a simple graph, connected graph, undirected. So there is no direction, undirected. So let's consider a graph which is simple, connected and undirected. A spanning tree of that graph is a free tree with v-1 edges that connects all the vertices. Okay, that connects all the vertices. But how many edges are there? If I have 5 vertices, 4 edges. 5 minus 1. So this symbol means number of vertices minus 1. That many edges I will have. So a spanning tree for a graph with the following properties. So what are the following properties? It's connected. I should not have cycle. A cyclic means it should not have a cycle. Okay, any traversal of a connected undirected graph visit all the vertices. The set of edges which are traversed during the traversal, it creates a spanning tree. So will be from the graph we are going to have a spanning tree. So spanning tree contains number of vertices minus 1 edges, and they are traversed during the traversal, and it creates a spanning tree. For example, let's look at the graph here. A, B, C, D, E, F, and the graph is here. It's an undirected graph. It's a simple graph, and it's a connected graph. What do you mean by connected? You have a path between every pair of vertices. There is a path between A to F, F to A, or D to E, E to D. There is a path between every pair of it. It's connected, it's undirected, it's a simple graph. So we will have a spanning tree, but the idea is this is the spanning tree given in the next figure. It's derived from breadth first traversal starting from the vertex B. So when you start from the vertex B, what is the traversal? Breadth first traversal from B to A, B to C, B to E, D to D, sorry, E to D and F. Or if you want to try the depth first traversal starting from C, so you get the spanning tree like this. So I told you already, if you have 5 vertices, you will have 4 edges. So here 6 vertices, 5 edges. Can you see 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Do you understand? Like previously I told you, spanning tree contains, let's say if it has n vertices, it will have n minus 1 edges. Okay, something like that. Okay. For an edge-weighted, connected, undirected graph, the total cost of the graph is the sum of the weights of its edges. So that's what we call minimum spanning tree for the graph with a minimum spanning tree. That means the total weight is minimum, very least total cost. What does it mean? Every edge has a weight, is it? When you add the weight of each edge, it will give you least total cost. What does it mean? Let's look at this graph. It's a connected graph. It's an undirected graph. It's a weighted graph. Weighted means every edge has a weight. Can you see? A to B, the weight is 2. The edge between B to C, the weight is 1. So every edge has a weight. So what is it minimum spanning tree? You have you apply any traversal and you get the spanning tree, but when you add the weight of each vertices, you should get the least cost. Okay, let's see the possible. So how many possible spanning trees we can get from this connected graph? 16 spanning trees. But let's see, oh, I can't provide all the spanning trees. So let's see some of them. This is some of the spanning trees given. Minimum spanning tree. What does it mean, minimum spanning tree? When you add the cost of each vertex, you should get a least number. For example, the first spanning tree, when you add them, 8 plus 4 plus 1, 13. And here 8 plus 3 plus 1, 12. Okay, here 8 plus 4 plus 3, 15. Okay, so you have you can get 16 spanning trees from the given graph, but the least total cost. So you will get 2 spanning trees. Can you see down there? The 2 spanning trees give the total cost 6. So this is minimum spanning tree. So you can find the minimum spanning tree for a weighted graph. Okay. So I uploaded one of the video for explaining the Prim's algorithm and Kruskal algorithm. So you may go through that the video explanation for these two algorithms to find the minimum cost spanning trees. So these two algorithms will be helpful to find the minimum cost spanning tree. So please view my 2 other videos explaining the Prim's algorithm and Kruskal algorithm. Thank you.